So Apache Parquet, the open standard efficient columnar storage format. I'm going to explain what these words mean in a few moments, but first, about me. I am a member of a project management committee of the Apache Parquet project. I have a similar role by the Apache Arrow project. I'm a CPython core developer. I've just started working at QuantStack, which is a small open source company from Europe. We specialize in data science and scientific computing. You can find my GitHub account, of course. So, first an overview of what Parquet is. So, open standard efficient. Why is it open? It's a community project that works under the rules of the Apache Software Foundation, which mandates some kind of open and public governance. So it's an open specification which is developed in the open. It's also several open source implementations which are similarly maintained by the same team of community volunteers. It's a standard which I would call de facto. It's not backed by an official body such as the IETF or the ISO, but it's still community-backed, and it's quite widespread. So I don't think you'll find any other file format with similar characteristics that would have the same popularity. On the other hand, if you look for open data on the internet, you will find that CSV is still very much ubiquitous, even if it's quite obsolete technically. And third, why is it efficient? It's efficient on three main metrics. The first metric is storage footprint. So Parquet allows you to compress your data quite well. It's efficient in terms of read performance. So you can read a Parquet file much quicker normally than a CSV file, for example. And it also allows for efficient querying, which means you can efficiently query some subsets of your data. Why columnar storage? So traditional database systems are row-oriented. This means that when you have rows of data, each row is laid out contiguously in memory. So in this example, I have a very simple example where we have 4 columns. One column is the name of a type of fruit. One column is the weight or the average weight of this type of fruit. We have a column with vitamins for each type of fruit, and a column with typical months in which you can consume this fruit. If you have a row-oriented representation of this, the entire strawberry row will be represented and laid out in a single piece in the file. So in a columnar-oriented storage, you will have one block of data for the name column, one block of data for the weight column, and so on. Modern analytics systems tend to use column-oriented storage, so you'll find column-oriented storage in things like DuckDB and other kinds of similar systems. Why columnar? Well, columnar-oriented storage turns out to be good for several reasons. The first is compression efficiency. If you look, each column has different statistic characteristics. For example, the name column is a text column, so if you represent all physical values contiguously, you'll get good compression ratios on this column. Similarly for the weight column, because it's a range of values that typically has a certain range, so given the right encoding and the right compression scheme, you'll get a good storage on this column, and so on. It's also good when you want to read a subset of columns. If you have a table with tens or hundreds of columns, you typically don't want to read all those columns. You're interested in a subset of the information. And so if each column is laid out contiguously, it allows you to not read some entire blocks of your file. And it's also good when you have computations over many rows. For example, typical analytical queries, you want to gain insight over your entire data set. So for example, you want to get the average weight of your fruit. So if the weight is contiguously represented in the file, then the average is very quick to compute over this column. So a high-level view of the features of the Parquet format. The first feature is that it has a rich data model. It's strongly typed with data types that reflect the common data that you can find in database-like systems or tabular data. You have typically numbers with different kind of temporals. You have strings and so on. It's arbitrarily nested. So if you look at this example, we have nested columns actually. The vitamins, you have several vitamins potentially. You could represent it as a text JSON object, but it's not very efficient. You can also represent it as a nested column with several child columns, for example, the C and A columns for those two vitamins. And the other months column is also a nested column of a special kind because each row can have a number of values. It's a bit like a list in Python if you want. So Parquet allows you to represent that logically in the schema. So it allows you to say that some values can be omitted. There can be nulls in SQL and SQL parlance, or the equivalent will be known in Python. There can be repeated values, so the months column here. It's friendly to writing to remote object stores such as S3 and GCS. When you write a file to S3 or GCS or this kind of remote store, you can only do it sequentially. You cannot go back in the file and say, oh, I'm going to fill out this part that I haven't written at the start. So Parquet is laid out in a way that it allows single-pass sequential writing. So you can write directly to S3 without going through a temporary memory area or a temporary local file. So this is very, very useful. When you're going to write a very large file, you don't want to create some temporary storage for it on your local disk. It also allows for random access. So random access means you can parallelize reads across columns, across pages. I will explain what pages are later. You can selectively read columns. You can selectively read some subset of columns. It has optional support for encryption. I'll also talk about it later. Well, let's point out that CSV has almost nothing of all this. So let's dive a bit deeper. What is in a Parquet file? First item, the data model. So as I said, the data model of Parquet is a nested schema. You can think of it as a tree of nodes. Each node is strongly typed. It can be either required, optional, or repeated. So as I said, optional means you can have nulls instead of values, and repeated means you can have a list of values in a given row. An important property of this is that only leaf nodes in the schema are actually tied to physical data. So the physical columns are the leaf nodes in this schema. In this example, I've underlined them in red. You have 5 physical columns. You have a name and weight, which are both top level. You have the A and C vitamins, which are 2 different physical columns. So they are going to be laid out separately in the file. And you have the months column, which has a nested element called element. And so each column has a specific data type, as I said. What are those data types? Well, first layer of typing, Parquet has physical types, which are very simple and very stable. They have been the same for the last 5 years at least. So you have 3 different kinds of integers, including deprecated int 96. You have booleans, floats, doubles, fixed length byte array. I think you understand it's a bit like car in SQL, and byte array is actually a variable length character array. A byte array without any attached semantics. So of course, these data types are a bit weak when it comes to representing actual data semantics. So there is an upper layer of typing, which is logical types. While each column must have a physical type, it may be optionally annotated with a logical type, and the logical type will tell you what the richer semantics of the data are. So logical types can also be parametered. So for example, we have a bunch of numerical logical types. You can represent integer types of different widths, 8, 16, 32 bits, 64. You can have decimal types, which you probably know about if you know just a little bit about SQL and other kinds of query languages and data representations. We have float 16, which is backed by a 2-byte fixed length byte array. We have various dates and times and timestamps, which can be parametered by their respective units, microsecond, millisecond, nanoseconds. And you can also say whether they are actually UTC-based or they are based on an undetermined local time zone. We have logical types, which can be backed by binary or string physical types. So string means UTF-8, actually. We have UID, which you know about. We have JSON and BSON, when JSON and BSON are just represented as their serialization. So nothing special here. And we have other miscellaneous logical types. I'm not gonna talk about them. So how is this all represented? First, we have optional values. How does it work when we have optional values in the column? Well, we're going to take an example. The vitamins column is actually two physical columns, vitamins.A and vitamins.C, and we can see that for each row in this column, there can be three situations. The first situation is that there is no value at all. At the top level, it's not defined. So, for example, the third one is left blank, it's null. A second situation is that the top level value exists, but the leaf value doesn't exist. For example, the first row, we find that in the first row there is some information about vitamins, but the vitamin A is absent, so it's a bit like a null. And the second situation is that the top level value is present and the nested value is present as well. So this is three situations, so we give them three values, 0, 1, and 2. And for each row, we call them definition levels. And for each row of each physical column, we write a definition level according to in which situation we are. So for example, if we take vitamins A, we see that in the first row, the top level object is there, but the A vitamin is not there, so definition level 1. Second row, the C vitamin is there, so really the inner level is defined, so definition level 2. And the third row, we see that there is no top level information at all, so definition level 0. And same for the last one. And as for the physical values, they are only represented serialized in the file if they are present. So while we have 4 definition levels in the first vitamins.A column, we only have 2 physical values which correspond to those definition levels which are equal to 2. And same for vitamin C with different values. Then how are repeated values represented? This is a bit more difficult to understand because we can have several physical values for a different row. And we are going to serialize the physical values as they arrive in those rows. So you see here we have 4 rows. And we have 6 physical values. How do we know which ones go into each row? Well, we have a separate structure called repetition levels. And the idea is that, so this is a simple example where there is one level of nesting. It can be more complicated if you have a list of lists, for example. If you have one level of nesting, you can have 2 different values for your repetition levels, sorry. It's equal to 0 if a physical value is starting a new row. So for example, April here is starting the first row, it has repetition level 0. May after April is not starting a new row, it's a continuation, so it has repetition level 1 and so on. And there is a special case here, the last row does not have a value at all, it's null, so it also has a definition level of 0. Sorry, yes? Yes, they are. Yes, I'll go over it in the next few slides. So this is the information about repetitions and definitions, but then there are the physical values themselves. The physical values have to be encodings, and the Parquet format supports several kinds of encodings. The most trivial one is the plain encoding. If you think about how you will naively or intuitively store integers and variable length strings and so on, well, it's just more or less like the plain encoding works. So it's not very efficient, but it's not very efficient in terms of storage, but it can be quite fast computationally when reading. We have run length encoding, which is run length encoding plus bit packing. I'll go over it a bit in the next slide. We have different kinds of encodings that are more or less efficient. Some apply to all data types, some apply only to a subset of physical types. And there are also some deprecated encodings that this table doesn't mention. So we're going to focus on one encoding called Øredev dictionary because it caters for a kind of data that comes quite often in the wild. Often in real-world data, you have columns that have a small cardinality, either because they are true categorical columns or they are not categorical columns, but still there are many, many, many duplicate values. For example, if you have a large table with first names and last names, chances are that you have many times the same first name statistically. So either you encode all those first names or those physical values separately, or you say, well, I'm going to encode only the unique values and then encode indices into these unique values. So this is called dictionary encoding. It's quite an intuitive mechanism. This means, for example, we have a column with colors, and there are 3 different colors. We separately first represent the different unique colors as a plain encoded array of physical values, and then we encode the indices into this dictionary. And when we encode these indices, we use the encoding name Øredev encoding, which, despite the name, is not only run-length encoding, but also bitbacks the values. Often your dictionary is not that big. In this case, there are 3 values, so you only need 2 bits per value. So not only if there's a repeated run, it will encode logically the information that we have a repeated run and save space. It will also save space by encoding, in this example, the indices over only 2 bits per index. So it's quite efficient. And so this comes quite often, even in some kinds of data where you will not imagine that it's actually useful. For example, sometimes for floating point data, it's useful to dictionary encode. After encoding, there is a second optional step that comes, which is compression. Unlike encodings which are tailored for specific physical types, compression is general purpose. So it really takes the byte stream, that's the output of the encoding step, and applies a general purpose compressor. So of course you have the uncompressed compressor, which is quite trivial if you can imagine. And there are various kinds of compressors which are standardized as part of Parquet. So let's go over them quickly. You have gzip, which is quite ubiquitous because gzip is available everywhere for every language, every platform, and so on. But these days it's underperforming. It's not really state of the art. There is Broadly, which is far faster than gzip as far as I know. There's very Snappy, which is really very widely used with Parquet for various reasons. The first is that it's quite efficient and quite fast. And it was implemented a long time ago in Parquet. So you also have Z standard, which you may have heard about, which is really efficient in terms of storage compression, and it's also reasonably fast. You have LZ4RAW, which is the fastest of all these compressors, and you have a last one called LZO, which you probably won't see in the wild for a simple reason. It's that the official reference is GPL licensed, so it's open source, but it comes with more restrictions than the Parquet libraries themselves usually. So this is really on the micro level how physical values are represented, but how is it all organized in the file? Well, if we zoom out a bit, we have a first level, which is still low level, which is data pages. Data pages, when you read or write Parquet files, they are the smallest unit of work. This is the unit of work on which encoding and compression is done when a data page is compressed as a single block. So this means that on the other side, when you read, you cannot really pick into a single value in data page. You have to decompress it entirely. The actual size of a data page in Parquet files will depend. It's typically quite small, but it depends on the writer configuration and on the typology of the data. You can count on them being smaller than 1 megabyte. Hopefully much less than that, and less than 2,000 rows. If you zoom out a bit again, you have column chunks. Oh, I forgot to say. So a data page contains the values, optionally the definition levels and repetition levels if the column mandates them. There are optional statistics that tell us, for example, the min and max values inside the data page, the number of omitted values, this kind of things, and there is metadata to describe the data page. If you zoom out a bit, you have column chunks. Column chunks gathered contiguous data pages from a single column. It also adds its own metadata to the top and its own statistics. And importantly, all data pages in a column share a single dictionary for each column chunk. So we are talking about dictionary encoding here. For example, this dictionary blue, red, green will be shared amongst all data pages in the column chunk. So the typical size of a column chunk, you cannot count it on having a given range of values. It can be unbounded. Usually, column chunks are quite large. You won't read an entire column chunk at once. Well, it depends on what you're trying to do. So, of course, a column chunk represents a piece of a single column, but you have many columns in a file, so you can have row groups. Well, you have row groups with one column chunk per column. And it doesn't come with additional metadata, but it's just a row group. Think of it as part of your table. A file can contain one or several row groups. This is purely a decision by the writer or by the application. One situation when it comes handy to have several row groups is when you want to merge Parquet files. If you have existing Parquet files and you want to consolidate them into a single larger Parquet files, well, it turns out you can just concatenate the row groups. It's a bit more subtle than that, but it can be a relatively quick process. So this can be used if you have some kind of data lake where you periodically create new data and you want to consolidate it at the end. And then we come to the overall layout of a Parquet file. So a Parquet file starts with a magic number, which is quite a common pattern. It has this number of row groups, one after the other, so from 1 to n row groups. It has a bunch of optional bits after that, which I will describe afterwards. And at the end, it has a footer, which has a magic number at the end. And before the magic number, it has a bit chunk of metadata, which includes this representation of a schema and various other information about the file. The idea is that when you write a Parquet file, as I said, you can write it purely sequentially from the top, from the start to the end, and you can even write it sequentially while generating the data. It means you don't have to have the data materialized entirely in memory when you write a Parquet file. You can just sequentially generate your blocks of data and write them iteratively. So as I said, this is quite friendly to S3 and so on. And what readers do on the other side is typically start by reading the footer. And once you have read the footer and decoded it, then you know exactly into which part of the file you can pick to have this or that column. This pattern of having a footer which you first read and then you can look up everywhere in the file is quite, well, you may know it from the zip file format, for example. So the optional bits that I mentioned here, there's one which is named the page index. So optional means you won't find them in every Parquet file. It's a decision by the writer, and it also depends on whether the writer implements that feature of the Parquet format. So one optional bit is the page index. The idea is that you want to optimize queries where we select rows depending on some condition on a column. For example, in this table of fruit, you want to select all fruit with a weight between 15 and 30. This means that if you know that in a data page you have only fruit with a weight higher than 50, then you don't have to read that data page, you don't have to decode it and decompress it. So you spare some time by completely pruning some parts of your file when reading. And another use case where you want to have some kind of index is want to do indexed access in the file. You want a specific row number in the file. So this is another use case that is not very common, but some use cases like to do that, and all the while minimizing the number of IOs. So ideally, you don't have to look up every data page in the file to read the respective statistics. You want to just seek into a single part of the file and have an index which is compact there. So the solution that was adopted by the Parquet format is that there is two structures, collectively known as the page index, which store per column data at the end of the file. And the first one is the offset index, which also allows this direct navigation to data pages. So this is the indexed access use case. And the second one is the column index, which stores statistics for each data page. So the statistics are mainly min-max values, but we also have other information such as the number of nulls in the data page, which tells you conversely the number of non-null values, histograms of definitional repetition levels. So the efficiency of a column index to accelerate queries, of course, is data dependent. It depends on how well sorted or how well clustered the data, the physical values are in the file. And it also depends on which queries you run. So I give you this reference to a blog post by some fine folks at Cloudera who explain a bit more how that works and what kind of results you may gain from them. Another optional bit which comes from a similar concern is bloom filters. So in this case, you want to optimize queries where you look for specific values exactly. For example, you have a species common and you want to look for cats. You want to look for several species, cats and dogs, but not rabbits. So you want to do subset testing and filtering based on that. So the solution that was adopted by the Parquet format is to store optional bloom filters for given columns. And again, they are stored contiguously so that you can look up the bloom filter in one go. So a bloom filter, if you don't know, is some heuristic associative container. You take the bloom filter and you take a query such as, is this value, is the cat value possibly in the set that's encoded in the bloom filter? And the bloom filter tells you either no, definitely no, it's not there, or yes, perhaps, but it might be a false positive. So it's useful in that if the bloom filter tells you no for a specific data page, then that data page cannot contain the value that you are looking for, so you don't have to read it at all, you don't have to decompress it, you don't have to decode it. If it tells you yes, perhaps, you have to look up in the page table, and it may turn out that the value is not there. So the efficiency will depend on the selectivity of the bloom filter selectivity, which is 1 minus the ratio of false positives. The selectivity will depend on cardinality of the data. The more distinct values there are in the column, the less efficient the bloom filter will be. And it also depends on the filter size you choose when writing the file. You choose a number of bits or bytes for a filter, and the larger the filter, the more selective it will be. But of course, the larger it will be to read, and the larger it will be to decode. So it's a trade-off. And the nice thing is that there's a well-known statistical formula that can exist when writing a Parquet file to choose the number of bits in your bloom filters based on what selectivity you want. So you tell the formula, I have 15 different values in this column. It can be an estimate, it doesn't have to be exact. I want to have max 1% false positive on my bloom filter, and it tells you, well, you should use, 4 kilobytes. So there is a much more complete blog post about this with some real-world experiments. Another optional feature that I alluded to at the beginning is encryption. So the Parquet spec has provision for optional whole file encryption, which has the classical 2 goals of ensuring confidentiality and also protecting against tampering. That is, if an attacker can write to this file and modify a few bits or bytes, then the reader will recognize, thanks to encryption, that the file has been tampered with. So the way it works is that each individual file component is encrypted independently. These file components are generically called modules in the encryption spec. A module can be a data page, it can be a piece of metadata, and so on. So the idea is that you can still do selective reads into a file. If you do naive full file encryption using a random general purpose encryption utility, you have to decrypt it in one go. Using per component encryption, as Parquet does, you can still retain the usual features of Parquet, such as random access and only reading selecting data pages depending on your query and so on. So it is based on symmetric encryption using 2 flavors of AES, either GCS or GCM or CTR. By default, it will use 1 symmetric key for the entire file, but you can also ask it to use per column keys, which in some elaborate use cases can allow for selective access. I don't know how much it gets used, but at least it's possible. So key management is out of scope with the actual encryption spec, but the implementations might help you actually manage keys, for example, using key encryption keys, master keys, and so on. So it can be quite flexible despite the Parquet format not providing direct support for it. And there is an elaborate presentation about it by Gideon Gershinsky, who actually designed the encryption spec. So this is the link to the talk. So yes, so we've seen this was a high-level view of Parquet features. And so now what about the ecosystem? The implementation of Parquet, you have 3 main open source implementations. The Java implementation was previously known as Parquet MR. MR stands I suppose, for MapReduce, because it stems from Hadoop a bit. It's known as Parquet Java now. There is the C++ Parquet implementation, which is actually a component of our C++, and therefore has bindings to Python, Ruby, R, and possibly CGlib and MATLAB. And there is Parquet Rust, which is also a component of Arrow Rust. There is a GPU implementation inside of QDF, which is also open source. And there's an unknown number, at least unknown to me, of proprietary or in-house implementations of Parquet. Additionally, Parquet is has available support in a number of libraries, engines, services. So, for example, DuckDB is able to query efficiently Parquet files. Spark, Pandas can read Parquet files. Dask also as well. It's a distributed computation system for Python. There's Iceberg, which is actually Apache Iceberg is layered over Parquet. It uses Parquet files with additional metadata. There was recently an extension to connect Postgres and Parquet, which was released, which is quite rudimentary. It allows you to use Parquet files as sources or sinks for the copy command, as far as I understand. And there is a number of crowdsourced systems which also support Parquet. And we also see the operation of domain-specific communities, so mostly GeoParquet, which is a community which has developed a set of soft conventions for embedding geospatial data in Parquet files. So what is the present and the future of Parquet? So Parquet is not perfect, it has limitations. One thing that comes up is that there are many features, as you've seen, and not all of them are supported by all implementations, or they might have been added recently in this implementation. So example of recent features that have selective support for now are LZ4O, the byte stream split encoding, which I haven't described, and Bloom filters. Writers, at least the open source writers, when you ask them to write a file, they are usually conservative in which features they choose to exploit, but usually you can also configure them. So the idea is that you know what your target user base uses as a Parquet reader. You can selectively enable the features that they support. A limitation that has come up recently, and especially in the context of machine learning, is that Parquet uses a serialization framework named Thrift, which is not terribly efficient. So when you have a very wide schema in Parquet, and wide means thousands of columns, metadata deserialization can be a bit costly, because you deserialize the entire schema at once when reading the file, and with Thrift it's not very fast. So these very wide schemas with thousands of columns come up in machine learning, where people want to have one separate column per parameter. Another limitation is that you don't have any random access inside a data page. You cannot pick into a bunch or a single value inside a data page. You must decode and decompress the data page as a whole, which is typically not very costly, but it's still much more costly than if you could pick directly into a value that you're interested in. The last limitation I know of, last major limitation, is that you cannot really store large binary values. If you have a column that's supposed to represent images, it's not recommended to store the entire image inside the column. So there are alternatives to Parquet. I'll cover two open source alternatives. Apache Orc, which has similar characteristics of being able to represent nested data with random access and so on. They made different technical choices, but it ends up that it's roughly as efficient as Parquet. Sometimes more, sometimes less, but it's more or less of the same concretely. The main difference with Parquet is actually the ecosystem, which is much smaller around ORC for different reasons, sorry. So I would generally recommend that you use Parquet and not Orc, because there doesn't seem to be any strong reason to use Orc. And there is another very recent alternative called Lens v2. There was Lens v1 before. It's a very innovative format in terms of its general design. It's extensible. It's also very recent. It has, I think, perhaps it's 1 year old or something. It's designed primarily for the constraints of AI workloads, so typically, for example, having very wide schemas. There are two very insightful blog posts about Lens v2, so I recommend you read it if you're interested. But Parquet is still actively developed. It's not dead. It's still not replaced by these alternatives. The latest format spec was 1 year ago, and I expect we're going to do another release in less than 1 year. We're more discussing, we're busy adopting a new variant type, which has been designed as part of the Spark and Iceberg projects, which allows to represent dynamically typed data, so things about document-oriented databases, for example. So you have things, some JSON, where there is some common structure among rows, but sometimes there is an additional field or missing field or something. And the variant type is meant to represent that efficiently, or at least much more efficiently than if you would just serialize the JSON. So it will be integrated into Parquet. There are discussions around solving the metadata deserialization problem using something other than Thrift. So typically it will probably use flat buffers. It's been experimented on for now. It's not yet decided, but I have good hope that in 1 year we'll have something. And it will still allow compatibility with older readers thanks to some encoding tricks. So there is quite some hope that it wouldn't break compatibility. An old reader could still read a new file. It will still not be much faster than it is today. So yeah, Parquet is still alive, and I didn't write it down on the slide, but there are also discussions around standardizing geospatial logical type. So I talked about the GeoParquet community, but the idea is to have a dedicated logical type so that we can encode statistics that are meaningful for geospatial data, such as bounding boxes. And there are also discussions around making Parquet more extensible. So that's it. I think we have a few minutes to discuss. Any questions? Yeah, so Parquet. Yeah, you don't use Parquet like a database. You won't mutate your file once you have written it. You won't mutate the data, and you won't mutate the schema. So you have to choose your schema upfront. So the answer is that you don't mutate the schema at all. Or at least not inside the Parquet file. Then you can perhaps build something on top of Parquet that will involve schema mutation, but it will use other mechanisms than Parquet. Anything else?